Hi, I'm Mark Barsamian. In this video, I'll be discussing compositions of functions. This material is from section 7.3 of the book. The corresponding homework is this set of 5 exercises from section 7.3. We'll be using some concepts from earlier sections. First of all, from section 7.1, the identity function on a set denoted capital I subscript capital X, where that symbol capital X denotes a set. Remember, that's just the function that does this. When you feed an input little x into that function, the output is little x. The function just produces as output exactly what you feed into it. And we'll be doing an example involving the floor function given by this definition. We'll return to that when we do that example. We'll be discussing examples of injective functions. Remember, the word injective is the same as one-to-one. I prefer injective. And what this means is that for all inputs, x1 and x2, if the resulting outputs are the same, then the inputs must have been the same. Or the contrapositive is equivalent. For all inputs x1 and x2, if x1 is not equal to x2, then the resulting outputs are not equal. We'll be discussing surjective functions. Remember that surjective means the same thing as onto, and what that means is for every element in the codomain, that is for every y in the set capital Y, there exists an element of the domain, at least one, such that if you use that x as input, you'll get that little y as output. We'll be discussing bijective functions. Remember that to say a function is bijective means the same thing as what the book says is a one-to-one correspondence. I really prefer bijective. So that's a function that is both injective and surjective. That is both one-to-one and onto. Another concept from section 7.2 that will be important is that of an inverse function. Remember that if a function is bijective, a function little f from set capital X to capital Y, if that function is bijective, then it will have an inverse function. That will be denoted this way: f superscript -1 colon capital Y arrow capital X. So f superscript -1 is called the inverse function for little f, and it's a map from the set Y to the set X. And it's defined this way. F inverse of Y equals X just simply means that f of x equals y. And we had this result from Theorem 7.2 that if f is bijective, then of course it has an inverse function, and the fact is the inverse function will also be bijective. Let's go on to the current material, section 7.3. Now, first of all, notice that there's a mistake in the book's definition. So in this definition, we're supposed to have f being a function from some set capital X to some set capital Y prime, and g being a set from set capital Y to set capital Z. And the relationship here is that y prime is a subset of y. As in this diagram down below, notice that y prime is this smaller set and y is this larger set. So little f is a map that takes input from the set capital X and produces output that's in the set capital Y prime. Whereas the function g takes input from the larger set. Anything that's in the larger set can be used as input to g and produces output in set z. So what's called the composition of f and g is denoted this way: g circle f. And it's defined this way. It's a function that maps from set x all the way over to set z. So this composition takes as input anything in this set x and produces as output something in this set z. And it's defined this way. We have to describe how you get the output. Here's the symbol for the function, g circle f. Here's the symbol for its red input. Now we have to describe how you get the output. The output of g circle f is obtained this way. You take that red input and you feed it into f, and you get an output here. And then you take that output and you feed that into g to get an output in set z. Let's do an example. Example 1 is similar to 7.3, number 4. Little f is a function from the real numbers to the real numbers, and it's defined by f of x equals x cubed. Little g is a function from the real numbers to the real numbers, defined by g of x is x to the 1/3. So find f circle g, find g circle f, and answer this question. Does f circle g equal g circle f? Well, first of all, notice that this says find this function. To give an answer to that, we have to describe the function fully. So we have to say what the function's domain and codomain are, and then how the function works. Now there's just the kind of the schematic form for the composition, but we have to actually give formulas for this. Now for this, it'll be useful to have the empty versions of our functions. So we get the result that f circle g of x is x. Notice that we use the empty version of f in constructing this expression, and notice that we use this rule of exponents in simplifying this to make it this, and then that just becomes x. Now let's find g circle f. So we get the result that g circle f of x is just x. And we used, for that calculation, the empty version of g. And we again use this rule of exponents. So notice that f circle g equals g circle f. Now remember what it means for two functions to be equal. They have to have the same domain, the same codomain, and they have to always produce the same output when they are fed the same input. So these two functions really are equal. So that's interesting, but what's also interesting about this is that it illustrates the following fact. If f is a bijective function, that is a one-to-one function, and its inverse function is denoted this way, then if you compose the inverse with f, you get the identity function, the function that when you feed in x just gives you x. Well, we know that this is the inverse function for this. G is the inverse function for f. So when I compose g with f, I get the identity function, the function that whenever you feed it an x as input, it just always spits out the same x as output. And it worked the other way as well. F composed with g is the identity function, because when you feed it an x, it just spits out an x. So this theorem says that always happens. If you have a function and you have its inverse function and you compose them, what you get is the identity map. Let's go on. Example 2 is very similar. F is this function from the real numbers to the real numbers, f of x equals x squared. G is this function from the non-negative real numbers to the real numbers, defined this way. G of x is the square root of x. So let's do question A. Find f circle g. So the result is that f circle g of x is x. Now notice the function diagram, the arrow diagram for f circle g. F circle g has a domain that is the domain of g, and it has a codomain that's the codomain of R. Now let's do question B. Find G circle F. Well, the thing is, G circle F is not defined. So this composition is not defined because F is a map from R to R, and G is only a map from R non-negative to R. So this codomain of F is not a subset of the domain of G. So I'm not allowed to write this composition symbol, just because of the way I've written the descriptions of F and G. So when you go back up to the definition of composition, the definition of composition was supposed to include this symbol, the range, or the codomain of F is a subset of the domain of G. Well, they actually said range of F, they didn't say codomain of F. So what they said in that definition is actually technically true, but it's misleading because this symbol is the codomain of F. We want the codomain of F to be a subset of the domain of G. What I'm getting at is we have to be careful about the way that we define our functions, the way that we write not only the function formulas, but also the function diagrams, the arrow diagrams that include the domain and codomain. So the way we've defined our F and our G, we're not really allowed to write G circle F. But this can be fixed. We can write F this way. F is a map from the real numbers to the non-negative real numbers, defined by the same exact formula. We're just acknowledging, we're noticing that the y values on the graph of f of x will always be greater than or equal to 0. So we can redo this example. The result of question A is the same as before. So the result is that f circle g of x is x. Now notice that this tells us that f circle g is the identity function on the set of non-negative real numbers. Because whenever you feed an x into that function, you get an x out. Now let's look at the map G circle F. Now notice that it maps the real numbers to the real numbers. Its domain is the domain of F, and its codomain is the codomain of G. Now here, you might be tempted to say that this is the same as x, but it's not. This is actually the absolute value of x. The reason is that this symbol stands for the non-negative square root. So let's do some examples. If you do G circle F of 5, you get 5. But if you do G circle F of negative 5, you don't get negative 5. The square root of 25 is the number plus 5. So G circle F of x is the absolute value of x. It's not the identity function. Let's answer question C on the next page. Does f circle g equal G circle F? Well, the quick answer is no, they cannot be equal. f circle g is a map from the non-negative real numbers to the non-negative real numbers. G circle f is a map from the real numbers to the real numbers. So they don't even have the same domains and codomains, so they can't be equal. So the fast answer is those functions are not equal because their domains don't match. But we can give some examples that make this even clearer. So we see that for some inputs, the outputs of f circle g and g circle f match. But for some inputs, the outputs don't match. For an input x equals -5, you don't even get an output from f circle g. And for g circle f, though, you do get an output. You get an output that's the number 5. So those functions are not the same. Let's go on. Example 3 is similar to one of your homework exercises, 7.3, number 7. Define the function f from the integers to the integers by f of n equals n cubed, and define g from the integers to the integers by g of n equals n mod 4. So question A is find f circle g of 3 and g circle f of 3. So notice that f circle g of 3 is the number 27, g circle f of 3 is the number 3. Notice that f circle g of 2 is the number 8, but g circle f of 2 is the number 0. So question C is easy. Those functions are definitely not equal. Let's go on. Example 4 is similar to your homework exercise 7.3, number 9. F is a map from R to R defined by the function, this should say f of x equals 3x. And G is a map from R to R defined by g of x equals the floor of x over 3. I'll write those in over to the side. So question A is to find f circle g of 3 and g circle f of 3. So we see that for the input of 3, x equals 3, the outputs of both functions are just the number 3. Now, let's compute the outputs for an input of 2. We see that for an input of 2, f circle g gives an output of 0, but g circle f gives an output of 2. So f circle g and g circle f are not the same function in this case. Let's go on. Now, not all compositions are difficult. If you compose a function f with the identity function, you just get the function f. So consider this diagram. F is a map from x to y. The identity function on y is a map from y to y. And you can see that composing f with the identity function has no effect on the outputs. So f composed with the identity function is just f. And similarly, if I compose the identity function with f, the other direction, I get f again. Now let's do this example. We have this set A, it's the set of all real numbers except the number 3, and the set B is the set of all real numbers except the number 1. So f is this function from A to B, and g is defined to be this function from B to A. Now let's give their empty versions. So those are the empty versions. Now let's find f circle g. First we have to describe the domain and codomain. The domain is the domain of g, and the codomain is the codomain of f. Now we have to give the formula. So notice that f circle g is the identity function on the set B. That is, if I feed in any x that's in the set B, I get out x. Now it's important that I feed in an x that's in set B, because I'm not allowed to feed in the number x equals 1. Observe, if I try to feed in x equals 1, I get division by 0. It looks like it would be okay having x equals 1, looking at the final result. But these expressions are not even defined when x is equal to 1. So I can't say that f circle g is simply the identity function. I have to say that it's the identity function on the set B. Now let's find g circle f. I'll do that on the next page. We start by giving the domain and codomain of g circle f. Its domain is whatever the domain of f is, and its codomain is whatever the codomain of g is. Now let's get the formula. So we see that g circle f of x is just x. So that tells us that g circle f is the identity function on the set A. So notice, put these together. We already found that f circle g is equal to the identity function on set B. Well, this illustrates the following theorem. Theorem 7.3.2 says, if you compose a function with its inverse, you get the identity map. Compose a function with its inverse. In this direction, you get the identity map on set X. You compose the function with its inverse in the opposite order, and you get the identity function on the map Y. Well, what we've just observed is we've got an f and a g that behave this way. Well, there's a missing theorem. It's actually, it should be presented as a theorem in the book, but it's not. It's just, it's part of an exercise, 7.3, number 28. And it's this theorem. If you have two functions that behave this way, if their compositions behave this way, then it turns out those functions are inverses. Well, remember, in the previous video, for content from section 7.2, we discussed this function f, and we found its inverse. And what we found was the following. In that video, we found the inverse function had this formula, f inverse of y equals 3y minus 2. Well, that's the same formula for g. G of x is 3x minus 2 over x minus 1. G of y would be 3y minus 2 over y minus 1. The thing is, g has domain B and codomain A and has that formula. And we had previously found that f-inverse has that domain and range, domain and codomain, and has that formula. Let's go on. Now I want to talk about compositions of one-to-one functions, or compositions of injective functions. If f and g are both one-to-one functions, if f maps x to y and g maps y to z, and they're both one-to-one, then g composed with f is one-to-one. So here's a diagram that illustrates that kind of thing. So here's a composition of functions. F is one-to-one, and g is one-to-one, and g composed with f is one-to-one. The converse statement is not a theorem, though. Suppose f and g f maps x to y and g maps y to z. It's possible for the composition to be injective without both f and g being injective. Let me give an example of that. Notice that g circle f is injective. That is, if you pick two inputs that are different, they always produce outputs that are different. So again, if g and f are both injective, they're both one-to-one, then their composition will be one-to-one. But the converse is not true. It's possible for the composition to be one-to-one without both functions being one-to-one. But there is a partial converse to the theorem that's a theorem. And this is not presented as a theorem in the book, but it ought to be. Here's the missing theorem. Suppose that f maps x to y and g maps y to z. If the composition is injective, then you can say that f has to be injective. You can't say they both have to be injective. Now, the proof of this is actually quite simple. It helps to recognize the contrapositive. So the contrapositive says if f is not injective, then g composed with f is not injective. So let's prove the contrapositive. So we suppose that f is not injective. That means that there exist two inputs that are different that produce the same output. That's just the definition of being not injective. But that means this. If I take these two things that are equal and we feed them into g, the outputs are going to be equal because g is a function. If you feed it this one input, you get out one output. So these two things are equal. They're the same element, and so their outputs are the same. So notice, we have shown that there exists x1 and x2 that are not equal, but g circle f of x1 equals g circle f of x2. So therefore, g circle f is not injective. That would be statement 5. Let's go on. Compositions of surjective functions. If f and g are both onto functions, both surjective, then g circle f is onto, is surjective. Let me give a diagram for that. So you see that these functions are both surjective, they're both onto, and their composition is onto. That is, every element of the codomain of G circle F, every element of set Z, can be achieved as the output for some input in set X. Let's go on. The converse statement is not a theorem, though. It's possible for a composition to be surjective without both F and G being surjective. Now, we've actually already seen an illustration of that earlier. Look at this diagram. The composition G composed with F is surjective. Every one of these elements of set Z can be achieved as an output for some input chosen from set X. But notice that this function F is not surjective. There is no element of the set X that will give an output of S from set F. So this is an example where the composition G composed with F is surjective, but F is not surjective. So let's copy this diagram and move it down there and put it on that page. So I'll copy this diagram and put it down below. All right, so we'll go down to where we just were and we'll find that diagram there. So that's an example of a composition of functions where the composition is surjective, but F and G are not both surjective. But notice in this diagram that G is surjective. So it turns out that there is a partial converse to the theorem that we can state. Remember, the theorem says that if you have two functions that are both surjective, then their composition is surjective. The converse is not a theorem. You can have two functions whose composition is surjective without the functions both being surjective. So that converse statement is not a theorem. You can see here's a counterexample that shows the converse statement is not a theorem. But this partial converse is a theorem. Suppose F and G are functions like that. F maps X to Y, G maps Y to Z. You can say this: if G composed with F is surjective, then G is surjective. The proof is straightforward. Again, we'll prove the contrapositive. So the contrapositive statement is this. So that's the contrapositive statement. If G is not surjective, then G composed with F is not surjective. So we'll prove that. Now, I didn't do this for the proof of the previous missing theorem, but I'll do this here. Notice that we know how this proof has to begin. So we have to say, suppose G is not surjective, and we somehow have to show that G composed with F is not surjective. Well, let's work forward. What does it mean to say that G is not surjective? It means that there's some element little z in set capital Z that cannot be achieved as an output from G. That is, there is no little y in set capital Y that will give such that G of Y equals Z. But that means the following. If there can be no y in capital Y such that G of Y is Z, then that means there can be no x in set capital X such that G of f of x equals Z. Because this f of x is a y, and there is no y that will work to give an output of Z. So there is no x in set capital X such that G circle f of x equals Z. So therefore, G circle f is not surjective. That's statement 5. Let's go on. Now there's a surprising result about inverses of compositions. Suppose f and G are both bijective. Prove that G composed with f is bijective. So we can say that the composition is injective because both functions are injective. We have that theorem. Theorem 7.2.3 says that if both functions are injective, their composition is injective. And we can say that the composition is surjective. G composed with F is surjective because of Theorem 7.3.4 that we just discussed. If two functions are both surjective, they're both onto, then their composition is onto. So G composed with F is both injective and surjective, that is both one-to-one and onto, so it's bijective. So we did part A. Now prove that that is a function. Well, since G composed with F is bijective, it has an inverse function, which is denoted G circle F superscript -1. Now, why do we know this? This is one of those theorems from the previous section of the book. Let's go way back to the start of this video. This theorem, 7.2.2, says that if a function is bijective, then it has an inverse function. So Theorem 7.2.2 is the theorem that we need to use. So we've done that. Now here's the surprising thing. Prove that the inverse function is this. G composed with F inverse is F inverse composed with G inverse. Well, we'll do that on the next page. So how do we do that? Well, the trick is the following. We're going to do a couple of compositions. So notice that if I compose in the following way, I get the identity map on the set X. Let's compose in the other direction. We'll compose in the other direction on the next page. If we compose in the other order, we also get that the composition equals the identity. So this thing, F inverse composed with G inverse, has the property that if I compose it with this thing in either order, I get, as a result, the identity map. Well, let's remember a theorem we had earlier. We have this theorem, the missing theorem, it's discussed in one of the exercises, that says that if you have two functions that behave that way, if you compose them in either order, you get the identity, then that means those functions must be inverses. So let's go back down. We have this green thing and this red thing that when I compose them gives us the identity in either order that we compose them. So that theorem, that missing theorem, tells us that those two things must be the inverses of each other. So our conclusion is, by that missing theorem, we can say that that red thing, F inverse composed with G inverse, and that green thing, G composed with F, must be inverses. Well, we already have a symbol for the inverse of G circle F. It's this. The inverse of G circle F is denoted by this symbol. So we've just found that the inverse of G circle F is this thing, F inverse circle G inverse. Now notice that in this proof we used a couple of things. We used this fact that was discussed earlier, that if you compose a function with the identity function, you just get that function. That's pretty straightforward thing. We also use the fact that if you compose a function with its inverse, you get the identity function. That's a straightforward thing. But we also used this key step here, which is associativity. Function composition is associative, so that means we can move those parentheses around. Well, that's the end of this example, and that's the end of the video. Thank you.